lecture, Christian Bjartli, very Norwegian name. So I set up some servers on my personal domain I want you to connect to. bjart.li, and the host names are Umuzi 1 through 5. I just want you to have the experience of connecting through to servers through SSH, because that's a very common thing to do. It's something you should... many of you might have done that already and have some experience with doing it, but I've set up quite a few different distributions, so you'll get to sort of feel firsthand what the difference between different distributions is. When you connect through the shell, connect through SSH, and you get different shells and different terminals. Most things will be the same, but there will be a few minor differences. I wanted to get a feel for that. Also, one of the servers is not a Linux distribution at all. It's a different flavor of Unix. So you'll see how that feels. Anyway, we're going to move on. Just remember, try and have a look at that problem set as soon as you can. And try and keep in mind what we covered yesterday, because we're going to use it today. There's one thing that I didn't get to cover yesterday that I had planned to. It's a small syntactical thing about the bash shell. So I'm going to switch over to the slides, and that's not it. Give me a moment. This is going to be it. And hopefully what you're seeing now is a slide called globbing. And this is one of those syntactical constructs that you'll use in bash and the terminal all the time. A glob is nothing but a simple asterisk. And you know, there are a lot of characters that have a special meaning in the terminal. We saw how the tilde, the wavy character, resolves to your home folder. A dot means your current directory. ... is the parent directory. A star or a glob or a wildcard or whatever you want to call it expands to all the files and folders in your current directory. That's very useful if you need to loop over a lot of files. So let me try and bring up my terminal here, and let me switch to a different folder since directory, since I'm in the wrong directory. Now we're in Umuzi. Now, I can't just use a glob like that because we haven't prepended any commands, so if we do that, we'll just get a command not found. It expands into something the shell can't understand. What we can do is use echo to just print to standard out whatever follows. If we now do echo star, echo glob, that's going to expand. The shell is going to expand that into a list of files in the current directory. So if I do this, here we go. It expands into arguments, arithmetic expansion, etc., etc. Lots of files that I prepared for today's lecture. Let's do ls, just to see. Here they all are. Now the thing about globs is that they can be used to match file names. So for example, if you want to match files that end in .txt text files, you could do glob.txt, and that would match text files. We don't have any of those in here, but we could use the glob to match anything that starts with, say, the letter C. And we get all the files that start with the letter C. Or we could get files that end in the letter E. And get all the files that end in the letter E. Now, the globbing will not match hidden files. That's important. So if you want to match hidden files, you'll have to prepend a dot, and it'll match hidden files. Now, we shouldn't have any of those here. Well, we actually do, because in the directory listing, you'll actually get an entry for the current folder and the parent folder, dot and dot dot. Okay, so that's globbing, and that's something we're going to see later on. It's actually something that you're going to need in your exercises today. Problem set number 3. So, after having seen this small syntactical little trick, very useful trick, we're going to move on to today's topic, which is bash scripting. We've been working in the terminal so far. The main topic of this entire course is the terminal, the Linux terminal. And you've been using the bash shell. So bash scripting or bash programming is nothing but formalizing the syntax of the shell, showing you how you can take full advantage of what the shell offers, and how to actually save whatever you do in the terminal into a portable format, a script which you can move between computers and send to your friends and save for later, which is why you would want a programming language in your terminal. So let's bring up our slides again and move on to bash programming. Now, what is bash programming? You've heard about the bash shell. The bash, as we've seen, enables us to run commands. And what is a program? Essentially, an application. It's a series of commands. A script is just a sequence of bash commands that you can either execute manually by typing the commands one by one in your terminal window, pressing enter, waiting for the result. Of course, that's a bit tiresome if you want to do a lot of things, if you have a lot of commands to enter. So you can also put the commands in a file and run the commands from a file. And that's a script. Now, we've seen a lot of features of the bash Linux environment. We've seen redirection of output, and we've seen how programs work, how they run, how they interact. Now, the entire point of bash is to connect all the applications that you have on your computer. It's taking advantage of the Unix philosophy that if you have an application, that it should be able to interact with everything else. So in essence, your entire computer turns into one massive computing environment that you can extend with new functions and new functionality by downloading new programs or making new programs. And part of the power of this is that you're not bound to using a single programming language. Say if you want to accomplish something in Python or in Node.js, you often have to stay within that environment. If you want to do something in Python, you either have to hope that there's a library that will help you accomplish what you want to do, or you have to write it yourself. With the terminal, you get to connect all these different programming languages and environments. You can take the output from a Node.js application and input it into a Python application, which sends it output to a C application, and so on. Everything is interconnected through the shell and through bash. So that is, of course, one of the reasons to learn bash. It's the kind of glue that binds together all your applications, and since part of being in the Linux and Unix world is that everything should be able to interoperate as far as possible, that's a very powerful tool. Of course, with a bash script, it's portable. You can install it on other Linux computers and run it there. And if it's well written, it should accomplish whatever you want it to accomplish wherever you run it. That means that you can use bash scripts to orchestrate services on different machines. It means that you can use it to configure entire systems. It's the kind of glue that really enables you to take something you do on your computer and do it on many other computers and servers and systems. Also, it turns out that a lot of external tools that you will see as developers or data scientists, they actually use bash scripting natively in order to accomplish many of the tasks that you need to do. So a very simple example is continuous integration and continuous development systems. I want to know, do you know about CI/CD? Is that a word you've heard about? Have any of you ever used a CI/CD, continuous integration, continuous development tool? Do you know what it is? It's new to some of you. No, you haven't heard of it? Test-driven. So no, it's not test-driven development per se, but it's it's become part of agile culture and agile development. You will often use continuous integration pipelines to run your tests. But what continuous integration and continuous development is a workflow where the code you write is tied tightly together with the deployment process. So whenever you write code and you push it to, say, your Git repository, an automated system takes over and recognizes, oh, someone pushed code here. What should I do? I should run some tests on it, probably automatically, and notify the team if anything happens. If it fails to build, if it fails its test, fails the tests that you've written, it'll send a notification to the people who should be notified. If it was a push to development branch, the code should be automatically deployed to the development environment. If it was a push to a master branch, it should get automatically deployed into production so the customers can see it. CI/CD systems are these pipelines that will take the code base and recognize whenever you make changes to it and orchestrate everything that needs to happen afterwards. Very, very common in modern software, in the modern software world. It's probably essential because otherwise you spend a lot of time doing these tasks that are easily automated, like building your code base, making it deployable, and deploying it. That's a process that has to be done over and over and over and over. And CI/CD pipelines, they help you automate that task. Now, the reason I mention this is because many CI/CD systems will be orchestrated using bash scripts. And I actually set up a very simple one for this very course. One that I've been using all the time. You see the slides that I've written for this course, they're written in HTML. And whenever I need to update the slides, I need to publish them online. I've made some changes locally, I need to push them onto the internet. So if I can just bring up the browser, I can show you very quickly how that's done through GitLab, which is what I've been using for this. So this is our repository. Let me see, can you see it? Hopefully you can see the browser window. This is the master branch. On the left side, there's something called CI/CD and pipelines. And whenever I push new code to the repository, a pipeline is run. Every single one of these rows here is an instance of a pipeline that was automatically run when I pushed code into the repository. And it has a couple stages: publish, which just moves the code or moves the HTML files where it needs to be, and deploy, which makes the files available online. And all of this is configured in this single file. And it's basically a 2-line bash script. It's basically 2 commands: create a public directory and copy files into it. And the CI system understands the rest, and everything is just pushed online. Very, very convenient. And this is a very simple instance of what you can do with CI/CD, but configured using bash. And it must save me so much time. Yes, it's a lifesaver. Whenever I need to make a single change to the slide, that that's on your screen right now. I open it in the text editor, make the changes, I push it, and everything just happens automatically. Great stuff. So yeah, I hope I've given you some subjective reasons at least why you should learn some bash scripting. Now, a script is really just a file which contains, in general, statements in any interpreted language. That is a language where you have a program that is able to understand the language and execute commands directly without compiling them down to bytecode first. So C is a language which would usually be compiled down before you interpret the commands, and therefore you wouldn't really call a C file a script. But JavaScript can be just run directly through Node.js. A Python file can be run directly through the Python interpreter. Ruby, Perl, Lua all work like this. So any file, or whatever you want to call it, a £, then an exclamation mark, and then a path to the interpreter that's supposed to run the program. What do you call that sign in South Africa, by the way? I know it has a lot of different names around. Some people call it a hash sign. Some people would call it a hashtag. Some people would call it a £. What do you call it? Now, anyway, if you do that, Linux will understand that what you have is supposed to be interpreted using that program. Either the bash interpreter in the bin directory or Python in the user bin directory, and that will make it possible to execute the file. So let's have a look at that. Let me bring up the terminal. I've prepared a couple of files here. I've prepared a file called Node.js. You actually call it a hashtag. That's interesting. That's the Twitter and Instagram generation for you. Has it really become that ubiquitous? Is it called a hashtag in general now? Anyway, let's open the file called Node.js. You can see that I've started the file with a shebang statement, which tells Linux to open the file in user bin node. And it's a very simple hello world program. Now, since this is a script file which has a shebang statement, you can make it executable. If I do LSL now, you'll see that every single file in this directory is executable, has an X permission set for everyone. So if I now run this script, Node.js, it runs as if it is a program. You can execute it. Similarly, we have one for Python. User bin Python is used to run this program or run this script. It prints hello from Python, and if we run it, hello from Python. So bash scripts are just like that, except they start with, let's open a random one, first one, shebang bin bash. So if you want to write the script and you don't really know exactly where the interpreter is on your system, you should know about the which command, which will tell you that. So if I switch back to the terminal, I know that I have Node installed because I can run it. Type Node and here's Node. However, I don't know where it is. Like that, which Node, and it'll tell me it's in user bin Node. Which Python, user bin Python. Which bash, user bin bash. Whoops, I managed to close the entire window. That was not intentional. Let me try and get the terminal back. Sorry about that. There we go. I think. Okay. Terminal's back. Okay, back to the browser and our slides. Okay, to use a script and make it executable, just do chmod plus x. We've seen this before. Okay, now on to bash scripting and the syntax. Here's a very, very simple program. It's an adapted version of Hello World. And it should be pretty obvious what it does. It just prints Hello Umuzi on the terminal, or rather to stdout, as we talked about yesterday. So the first thing you ought to know about is, of course, comments. You can see that you can add comments using a hashtag. Don't like calling it that, but I'll call it that out of respect. You can either add it to the beginning of a line, or whenever the bash interpreter encounters a #, a hashtag, it'll interpret the rest of that line as a comment. So you can see I added the comment after Hello Umuzi. Nothing will get printed except for Hello Umuzi. Now, in a bash script, any line, any statement that you write can be any valid program invocation that you would be able to type in your terminal. So the way that we've run ls and echo and lots of different programs, make dir, wget, any of those can be typed on a single line, and they will do exactly what they would do if you ran that in your own terminal window. So for example, I think we've seen echo already. Echo just prints to standard output. So in order to get the script to print something, just use echo. That's the simplest way of outputting text to standard out. There's also another program called printf, which is also in the POSIX standard, which has slightly more options than echo. If you need that, you'll find out more about it in the man pages. So let's bring up the terminal. Let's find this very script. I think it's called Hello Umuzi. Here it is. And feel free to follow along on your own computers here. Type this out in a file and save it and try and run it. So I'm executing the file by, as you remember, prepending a period, a dot, slash. And that is because if I just try and run it like this, the terminal is going to try and look in the standard binary folders in /bin or /userbin in order to find it, but it's not there. It's in the current directory, which is why I prepend dot slash. I execute it. Sorry, I was going to execute Hello Umuzi. I executed the wrong file. That's the one. Hello Umuzi. Just like we should expect. Now, of course, it wouldn't be a proper programming language unless it had variables, and bash does have variables. They're very simple to use. You just follow the syntax on the screen there. Variable name equals, and then a string. Now the thing about bash is that it's not like many other programming languages that have data types. There's only one data type in bash, and that's string. Everything's a string. You can, however, interpret a string as a number when you need to. Basically convert the string to an int. But in everyday life, you should think about everything that happens in a bash variable as being manipulations of strings. So that also means that you should usually remember to put quotation marks around whatever you assign to your variables, because whenever bash encounters a space, it's going to think that the string has ended unless you put quotation marks around the entire thing. So in this test script we have here, we set the text to Hello Umuzi, and then it'll echo the text. Now there's two ways of actually referring to variables. And as we've seen before, we've seen some special bash variables already. We saw question mark, for example, which refers to the exit status of the last command you ran. You access variables by prepending a $, and really there are two ways of doing this. You can prepend it directly, as you can see at the bottom of the screen there, just $text. But it's become very common to use the full syntax, which is $, curly bracket, text, and curly bracket, or variable name in general. And there are several reasons for that, but one of them is that you can use the first syntax, the one with curly braces, inside strings, inside character contexts, and Bash would not get confused by that. You could print $, curly bracket, text, curly bracket, and something else, and Bash will be able to interpret it. In the second instance, let me actually show this in the terminal. It would make so much more sense probably to show it. Let's set text equal to Umuzi. Now I can do text Umuzi people in a single word, in one word. That would work. And this would, of course not. That's not a variable we know about. So yeah, that's one reason. So yeah, let's maybe run this application as well. Bring up the terminal. We should have one. Let's see what we call this file. Hello, Umuzi. No. Maybe I did not create a file for this one. Prompt name. No. Okay. This is, type this up yourselves and try and run it in your terminal. Pretty simple application. Pretty simple script. Moving on. If you try to access an unset variable, Bash is not going to complain. It's just going to evaluate that to a blank string, as in no characters. That's different from other languages, which might tell you that you're trying to access a variable that doesn't exist. That generally doesn't happen in Bash. So we can have a look at that. Here is a script where we're just accessing a unset variable. This variable is not set. Unset variable. Let's run it. This variable is not set. Blank string. Now, if you need to get user input interactively, there is a command you can use for that. It's called read. And in order to use it, you just use the syntax read and then the name of the variable you want to read into. So, if we look at the terminal again, here's this application, or this script. What's your name? Read that into name, and then we say hello. Pretty simple stuff. What's your name? Christian. Hello, Christian. Just like we'd expect. Now, what happens if you need to deal with variables in your script that might not be set? There's actually a syntax that you can use. And it's also another reason for using the curly braces approach to accessing variables. What you can do is you can, inside the curly braces, add colon, dash, and then the default value. In which case, if the variable isn't set or it's empty, it'll replace it with the default. So let's have a look at that. Here it is in the terminal. What's your name? It tries to read it. If I provide a blank answer or no answer at all, it's going to assume that my name is Umuzi. Let's try that. It's asking me for my name. I'm just going to provide a blank answer. And there we go. I got the default back. Now, we need to mention the environment. The environment is a very important feature of Linux and running applications in Linux. This actually goes for Unix in general. And that is that every process has a so-called environment attached to it. And that is a collection of variables that behaves pretty much exactly like bash variables. Your shell has an environment. Every process that your shell starts has an environment. Every application. And the environment is usually used to pass information to the application from the outside. Usually and often when you start the application, but sometimes also during runtime. So in order to see the environment of the running terminal, you can type env and it'll provide you with a list of variables. And these are variables which have been set by the operating system or other applications that are running that provide information to the shell about how it should behave. So here you can see it tells me that the current shell is bin bash. It has a shell variable set. Home is set. That's the home directory of the current user. The current directory I'm in is also set as a variable, the current user, etc., etc. Now, whenever you run an application or whenever one application spawns another application, which is basically what your terminal does, your terminal is an application, which whenever you type a command runs another application. Whenever that happens, the second application will inherit the entire environment, which means that it will inherit a whole lot of different variables. So whenever we're in a bash context, we can also refer to variables in the environment just like any other variable. Now that does not mean that any variable that we use in a script is written to the environment. That's not true. It's just that environment variables and local variables are accessed the same way. So let me try and find the script for you. Any questions so far, by the way? Or does everything make sense so far? Well, it seems like I haven't provided this script, so I'm just going to type it up real quickly. Bash. Let's try and echo our present work directory. Let's echo user. Let's echo home. All of these variables should be provided by the environment. And if we run it, voila! They weren't set inside the script, they were inherited by the outside process, the terminal that ran the script environment. Everything makes sense so far? Well, that's good. That's good. It hopefully should. Now let's move on. So if you have a bash variable that you do want to make available to other processes through the environment, that is possible. there's a keyword for it. It's called export. So whenever you have either exported a variable or set the environment in a different manner, we'll not talk about how that is done, that will then become part of the environment and inherited by every sub-process. So, as you can see here, I've illustrated how this would work if two scripts interact. The first is a script which refers to two variables, one called exported name, which should be exported from the script that calls it, and one called unexported name, which should be left blank because it shouldn't be provided anywhere. Then we have a second script, one which exports exported name and then calls print name. So let's find the script. Let's bring up the terminal. The first one is the one called print name. That's the one that refers to exported name and unexported name. And then so these files were written very late last night, so I apologize for not having sorted them. It's probably the one called export name. There we go. We're here exporting exported name, which should make exported name available through the environment, as an exported name will be set as a variable on the current environment. When we call print name will inherit the entire environment of the calling process, which is this shell, this script, and it will find the name exported name. It will find the variable as an environment variable. However, unexported name here is set, but it's not exported and it will not carry over into print name's environment. So let's run this. Export name, and as you can see, it says hello URI, because URI was the exported name, and the next one isn't found. Now there is one other way of exporting an environment variable to a program or application or script that you're running. And this is something that you can do during, of course, a normal invocation of the terminal. If there is a program you want to run that expects to see a certain environment variable, you can invoke it by just setting the variable on the same line as you invoke the application itself. So in this case, I'm just exporting the name Peter as I am invoking print name. That will not set exported name on my current environment, but it will set exported name as a variable on the child process's environment. So if we run print name, right now it will just print blanks because it hasn't been provided any names. Let's now do exported name equals Peter. And there we go. However, we will not be able to find exported name on our current environment. See, it's blank. Then, moving on and still talking about how you invoke programs and scripts, we need to talk about arguments. When you start a program from the terminal, everything that you write after the program name will be provided to the program as arguments. And we've looked into this. We've added parameters to ls, for example, by providing -l and -a as arguments to the command. So they modify what the command or what the program will do. And they are therefore important. And usually when you write scripts, or very often when you write scripts, you might want the user to supply input through arguments. Now, the thing about bash is that unless you tell bash otherwise, white space separates arguments. Which means that if you just type a string of words and nothing else, then bash will interpret every single one of those words as a separate argument. Let's see what that means. So take echo, for example, a very simple command. What it does is to take every single argument it gets and print it to standard out. So if we now write hello Umuzi, it'll print hello Umuzi. However, if we now add lots of spaces, what will happen? The spaces disappeared. Why did they disappear? The reason is that bash interprets what it saw here as, well, that's the first parameter. Then it just saw lots of spaces, and they just indicate that there's room until the next parameter appears. And the next argument, that's Umuzi. Okay, well, we told it to print hello and print Umuzi, and it did. So if we want to make sure that bash understands that hello and Umuzi belong to the same argument, they're just one string, we have to put quotes around it. And there we go. Now it actually did understand that hello Umuzi is supposed to be interpreted as a single argument, and the spaces are part of that argument. Now, another thing you need to understand about quotations in bash is that there's two ways of doing this. You can use double quotation marks, or you can use single quotation marks like this. And they seem to behave very similarly, but there is an important difference. And that is that if you use double quotation marks, then everything that happens inside of this argument, inside the quotation here, will be interpreted by the shell. So if I, for example, refer to a variable that exists in the environment, pwd, present working directory, that will now be interpreted. Hello, present work directory, Umuzi. However, if I use single quotation marks, that does not happen. So yeah, if an argument contains white space, you have to enclose it in double or single quotes. And with double quotes, you get substitution. With single quotes, you don't. Now you can refer to arguments inside your bash script, and they're referred to by number. However, the first number available, 0, is already taken. Variable 0 actually contains the name of the script itself, as in the file name. The command line parameters, the arguments, will be available from number 1 and up. So let's have a look at how that works. Here's my terminal. Here's the script that you saw in the slides. It refers to the first argument, the second argument, and it refers to all arguments. The @ sign is special. It'll actually concatenate all the arguments into a single list. In case you, for example, want to loop over all arguments in a for loop, which we'll look at later. But now let's try and run the script. Arguments. Let's provide a first argument, hello, second argument, Umuzi, and I don't really need to use quotation marks now, but I am. And it says that its name is arguments. We knew that. The first argument was hello, second is Umuzi, and all of them, hello, Umuzi. Now we could make this one argument. We could add another argument here, just the string 100, and let's add a third argument, which is not seen by 1 or 2. There we go. My first argument is hello Umuzi. That includes the space between hello and Umuzi because we put hello Umuzi in quotation marks. Second argument is 100, and all arguments that entire string. Okay, so now we looked at how we can assign static text to a variable, or how we can get static text input from a user by using read, by using the environment, and by using arguments. Now then, what happens if we want to use the output of one command, assign it to a variable, and further process it? That is possible through what's called command substitution. And that's when you basically take everything that's printed to standard out from one command and you save it. The syntax is $ bracket command end bracket. Another syntax that you'll often see in older scripts is one that uses backticks. Backtick command backtick. But that has been deprecated. And that's actually pretty good because scripts that used backticks and single quotation marks and double quotation marks everywhere were just horrible to read. This is, I think, a much more readable syntax. So let's have a look at how that works. Let's bring up this script, which should be called command substitution. Let me see if we can find it. Now, while I'm looking for the script, any questions? Anything that's not clear? Are you tired? Anything? And again, I apologize for having to actually sift through my directory to find out where the files are. Okay, and for some reason, seems like this isn't available. So let's then do it live. Let's do it live. Name, let's set that equal to who am I, which is the command that prints who you are. And let's set current time equal to date. And I should be careful, that should be the right kind of bracket. Echo hello name. It is current time. Okay, what did we do? We assigned who am I, and oops, wrong syntax. With command substitution, we want $, ordinary bracket, ordinary parenthesis, command end parenthesis, and that's what we've got here, I think. And we assign it to the variables name and current time. Okay, let's chmod this. Substitution, okay, and let's run it. Hello Christian, it is whatever time it is. Okay, now we've talked about exit status already, as in whenever a process exits and it encounters an error or a fault or something that it insists shouldn't have happened, it will save its exit status in the question mark variable. Now, whenever you assign something through command substitution, what you ought to know is that the same thing happens, and the exit status is going to be the exit status of the command you ran inside the command substitution brackets. So we have an example here where, let's go through it line by line. We're trying to assign to root files the output of ls/root. What does ls/root do? It tries to list the files in the root user's home directory. Remember, the root user has his own home directory, which is not under /home. Root is special. Of course, if I try to run this as an ordinary user, I should get an error. Now, what we've also done here, if you remember from yesterday, we've redirected the output from standard error to dev null. What does that mean? That means that if the program, if ls, tries to print any error output, we're just discarding it. We're just printing it or redirecting it to the null device. Now, what I can see here is that the syntax on the slide is slightly wrong because the redirection should happen inside that bracket. So mentally, please move the right end parenthesis after root until right before the quotation mark. Does that make sense to you? The redirection, of course, has to happen as part of the command. And when I typed up this slide, I seem to have made a syntactical error. Do you understand what I mean? Can you please say yes or no, so I know if we're all on the same page? So I'm claiming that, let me just switch to the right window. Here, this bracket here should be moved all the way over here so that this becomes part of the command that you're running inside these brackets. Sorry about that. I'll fix the slide when I get around to do it. Now, the next thing we're doing is to look at the exit status of the above command. The exit status should be 0 if we're running as root, and it should be something else if we're not running as root. So let me see if I can find the script. And goody, I have it. And yeah, guys, yes or no? It would be nice to get some feedback. Are we live or are we not live? So here we go. Here's the same script. As you can see here, I fixed the syntactical error. Everything is now inside the bracket. We're checking the exit status, and on line 5, we're printing roots files if we can get them. Otherwise, we'll print a default message. Remember the default message syntax, the default substitution syntax, which is : dash, and whatever the default should be. Okay, so this script should hopefully make sense in its entirety. We've seen everything that's needed to understand it. Command substitution, output redirection, exit status, and default value substitution. Let's run it. Now I'm running this script as my user. I don't have access to root's home directory, so it'll tell me exit status of ls was 2, and I do not have access to his files. However, if we run sudo suddenly it works, and I can see that there's a single file in root's home directory called Umuzi. Okay then, now we talked about how variables in bash are always strings. Well, sometimes you need to interpret those strings as numbers. And there is a syntax for interpreting a string. Remember, everything's a string, as a number. And that's the so-called arithmetic syntax, or arithmetic substitution syntax. And it's a mishmash of brackets, as everything is in the bash world. You'll just have to get used to this. Whenever you see some kind of special bracket, it has a purpose and meaning, but you need to have seen it or studied it in order for it to make sense. Now, the arithmetic syntax is made up of double brackets, $, double brackets, and double end brackets. And you can see an example that should hopefully make clear how they work. If you enclose variable names inside them, they will work as if they were integral numbers. So I have an example here where we've set the variable TWO to 2 and THREE to 3, and we're referring to them first as strings in these echo printouts, and then we're using arithmetic substitution to actually do some arithmetic on them. So you have addition and subtraction, multiplication, and you can use literal numbers. As you can see in the fourth echo statement there, I'm adding 7 to the variable TWO, 7 plus 2. And we'll also see how division works. Now, bash only works with integral math. That means there's no floating point arithmetic. You don't get to do 2/3 and get 0.67. Instead, you're getting ordinary rounded down integer division, where 2 divided by 3 is 0, and it leaves a remainder of 2. If you need floating point arithmetic, you're going to need to invoke some program that has that. So, as an example, I'm piping the string 2 divided by 3 to the tool BC. BC is a simple calculator thingy. It does more than just calculations, but if you wanted to do floating point arithmetic, you have to add -L. Otherwise, it behaves just like bash. BC-L provides floating point arithmetic. I pipe a string to it. The string is literally 2/3, which is interpreted by BC, which prints the result of doing that calculation to standard out. And we're using command substitution to take that result and put it into the variable called result. At the end there, we will actually get the floating point result. So let us now run this script. And I really hope that I have it, and it seems like I do. Here's the terminal. Here's the script. We've been through it now. Let's run it. So 2 plus 3 is 5. Looks right to me. 2 minus 3 is -1. 2 times 3 is 6. 2 plus 7 is 9. And as we can see, 2 divided by 3 is 0 because we're working with integer arithmetic. Now, if we run it via BC, you can see that we can actually get floating point results if we need them. 2 divided by 3 is 0.6, etc., etc. And now we get to control flow. Bash is like any other programming language. It provides control flow and conditional statements like if. Of course, one of the most important logical statements you need in a programming language. Now, if can be used in two ways. If you provide if before an invocation of a program, it'll run that program and it will look at the exit status. If the exit status was 0, which is what it should be if there is no problem, it will execute the then clause. Otherwise, if it encounters a non-zero exit status, it's going to either do nothing, or if you provided an else clause, it'll run whatever's in the else clause. So the syntax is if, then the command you're running, then some more bash commands, else, more bash statements, and the whole thing is bookended by if in reverse, phi. Now let's try and run this. Now let's see what we're doing here. We're again trying to access root's files by doing lsroot. And of course, either we can do that or we can't. And if we can, then it'll print that we were successfully able to read root, and the files are wherever the files are. Then I've actually added another statement, exit 0. And what that does is to actually terminate the script with exit status 0, which means that any application which uses my script, any other script which uses my script, can look at the exit status of my script and see everything went all right. If it didn't, then we can set a non-zero exit status, and that will be interpretable by whoever called my script. So let's try and run this. Let's see. Here's the terminal. Here's the script. We've explained it. Let's run it. I'm not root. So it says the script is unable to read root, exit status 2. Well, that was the exit status of ls. However, my script exited with exit status 1, which is what we see here. If I run this as sudo, successfully read root. Oh, by the way, you can see that I used a nice bash shorthand here. So exclamation mark refers to the previous command you typed. So I typed conditional root. I ran the script conditional root. However, since I didn't want to type everything again, I just wrote sudo exclamation mark. It's a nice shorthand to know. Right here. Okay. Moving on, and we're almost done. If you're not running an application, the if statement also accepts tests, and there are many tests that you can run. This is just a small selection of the tests that you can run. If you're interested in finding the full list, just search for bash conditional statements or bash and if on Google, and you'll find a more comprehensive list. But what you can do is, for example, check if a file exists. That's -e and file. And yes, these tests, they are also encased in some combination of brackets. In this case, 2 square brackets to the left and 2 closed square brackets on the right. Now, what you ought to know about this is that this is actually one place where Linux is not POSIX compatible. The square bracket if test, that's not part of POSIX. That's a Linux extension. POSIX and other Unix distributions, they have a syntax where you can run conditional statements and tests inside single square brackets. So just imagine replacing every single double bracket here with a single bracket. That would be a POSIX compatible syntax. However, due to some strange ways of interpreting syntax on the inside of square brackets, Linux has changed how substitutions happen in a way that's not POSIX compatible, and I'm not going to explain the minute details of that because it's not needed. What you need to know is that use double square brackets wherever possible. It'll make your life easier. Trust me. If not, go ahead and use single square brackets instead, and you'll quickly find out where things differ. Now, that of course means that if you write a script that uses double square brackets, you can't expect it to necessarily be possible to run it on anything but a Linux computer. Although it is, if Bash is installed on any other Unix distribution, if any other Unix distribution runs Bash, then the script should be portable. Now, anyway, the tests we're looking at here are -E to see if a file exists, -D to see if a directory exists. You can see if a file is readable or executable, or you can check any other permission. You can check if two variables are equal as strings. You can see if a variable is alphabetically before another, if you list them in an in lexicographical or alphabetical order, and you can check if a string is empty. You can also compare strings as if they're integers. -EQ, -LT, -LE, that's equals, less than or equal to. And of course, you can do some Boolean algebra here. You can negate an expression to get the logical negation. You can add logical and logical or, and they are expressed as double ampersand or double pipe. Here's a quick script which will illustrate what you can do. This one will check if the root directory exists. It'll then check if I have execute rights to that directory. And then the last one is a combined check. It'll check if I have execute rights on root, and if the root folder then contains the file Umuzi. So let me find that script. It's available here in the terminal. Let's run it. So, since I'm a normal user right now, there's only one condition that evaluates as true to me, and that's the one that checks if root exists. Right? Because I don't have execute rights on root, and since I don't have execute rights, I certainly also have execute rights and can see the file Umuzi inside it. So yeah, that looks about correct. Let's run the script as root. And everything now evaluates as true. Now for for loops, they exist as well. And the syntax is, as you can see on the slide, for variable name in list of numbers or list of whatever. Do. And then inside that clause you can refer to whatever instance of the variable as the name you gave it. Now you can recognize here that in the second for loop I'm referring to every single argument that I provided. We saw that earlier on when we looked at arguments. The @ sign refers to every argument. Now in Bash, that's actually a list. And if I want to loop over a list, I have to enclose it in quotation marks for reasons that I do not want to discuss, but that you can look up yourselves in the literature that I provided at the end of the last slide. However, if I just want to provide a list of things to run through as a variable, the way I've done it here, I've got 5 numbers that I want to loop through. I set those in a variable and I separated the individual instances with spaces. Then in that case, remember not to enclose the variable name inside inside quotation marks. Do not do that, because that will not work. Let's have a look at that. Let me bring up my for loop script. In the terminal, this is exactly what we saw. I'm going to run it without providing any arguments. For loop, and it prints 1, 2, 3, 4, 5. Now, what happened if we put quotation marks around it? What would happen then? In that case, it just sees a single variable with spaces in it. So it loops through once. It found a single variable, a single instance, namely the string 1 space 2 space 3 space 4 space 5. Therefore, we'll have to remove them. Okay, now let's add some arguments. 1, 2, 3, 4, 5. And it found some arguments. 6. Umuzi. Yeah, there you go. For loops. Now, if you ever need to generate a range of numbers, which you sometimes might, there's a syntax for that. Again, with brackets and braces. This time, as you can see, it's curly bracket, 0, dot, dot, and number, end curly bracket. Or if you want to do it in steps of 2 or 3 or whatever, you do another dot, dot, and the step size. Let's have a look. Here it is. First, we're just counting from 0 to 10, inclusive. Here, we're counting from 0 to 10 in steps of 2, and 0 to 10 in steps of 3. Whoop. Okay. And it looks like it did. Counted from 0 to 10 in steps of 1. Then 0, 2, 4, 6, 8, 10, and 0, 3, 6, 9. Now, there's while loops that you should also recognize from other programming languages. While loops continue running until the condition it evaluates is false. So a while loop in Bash works very similar to an if statement. You can provide it with a program name, and in that case it'll run as long as the exit code is 0, which is the equivalent of true when you run applications and programs. It'll also accept tests, and it'll continue until the test is true. So I've included a small example. It sets an answer variable, and then it wants me to say please. And it continues to read my answer into answer until my answer is please. So yes, this is basically my mother in script form. Let me see if I can find it. Here we go. And let's run it. Say please. No. Say please. No. Say please. Please. Thank you. Okay, have a look at that in the slides. That should hopefully make sense to you. And that's it. Now we've been through a lot of different bash syntax. These are the very basics. You should be able to accomplish quite a lot in bash just using what we've seen. Using variables, using the environment, being able to read input from users, being able to pipe from one command to another. And I've created a problem set for you which should exercise various ways of accomplishing things in bash. And one of the things, the last exercise I made is actually an exercise that I think is useful. Teaches skills that it solves a problem that you might actually encounter in real life. Of course, the best exercises actually do that, but in the academic world that's not always true. In this case, I think it is. So let me show you what I mean. If you remember from yesterday's problem set, I asked you to download a file which is basically the top 100 books in Project Gutenberg is text files. And if you downloaded that file and extracted it with tar, you should have this list of files. Now these are books from the Western canon, mostly. But they have just horrendous names. Let's bring up one of them, 16-0. I have no idea what that is, but apparently that's The Awakening in Selected Short Stories by Kate Chopin. And PG2097, what's that? That's Sign of the Four by Arthur Conan Doyle. Oh, interesting. Now, anyway, once you have something like this, you'd like to clean it up. Either because as a programmer you like to keep things neat and tidy, or as a data scientist you need to clean your data up. Well, what would be very nice was if we could extract the title of every single file and rename those files using the actual title of the books themselves. That's what exercise 6 on today's problem set will guide you through. Once you've done that, you'll get a nice directory which looks like this. Here you can see all the files actually have names that make sense. The Sign of the Four.txt, Souls of Black Folk.txt. This should be accomplished in a few lines of bash code. And today, I think the instructors today will be able to guide you through that exercise. I think if you don't get time to do it today, do sit down and try and do it when you get time. It's a great exercise. It'll show you what bash can be used for in everyday life. So there we go. That's bash scripting. It's been a whirlwind course. We've gone through tons of information about Linux in 3 days. I hope this has been useful to you. I hope this will enable you to go and learn more about Linux if you want to, or you have to. Hopefully the first. I'd say hopefully the latter as well, because I think Linux is a great operating system and a great environment to work in. So I hope I might have shared some of my enthusiasm for it as well. But there you go. Thank you very much for following me these 3 days that we've had together. I hope it's been as fun for you as it's been for me. So yeah, there we are. That's the end of Umuzi's intensive Linux course. Now then, any questions, any comments? Anyone who feels like they've learned something or haven't? Anyone who feels like things could be done differently? Well, thank you, Uri. I appreciate the... I'm going to interpret that as a standing ovation. Because I can. Well, excellent. I hope you'll be provided with problem sets. All the slides are going to be available online, and they'll stay available, so whenever you want to look back at these slides, they'll be online. They'll stay online. If you want to get in touch with me, please do send me an email. Uri and Peter and the rest, they have my email address. Actually, I should have been given an Umuzi email address, and that still hasn't happened. So please get on that, guys. I'd be really happy to hear back from you. Even just see a photo of you. I haven't seen any of you guys. It'd be nice to see a photo, see who you are. Now, until next time, if I see you again, thank you very much. And bye-bye.